Start. So dear student, I Rakesh Jain from Gyanwar University. Today I am going to teach you about the basic semiconductors. What is the meaning of semiconductors, why we use them, and from which materials they are made from, how many types of semiconductors, what are their internal constructions, how they build, how they classified, and in those classifications, how they work, yeah, how they use, which kind of devices they are using for. So now, first of all, just see the types of the meaning of semiconductors. Semiconductor. Now I am writing down here. Now, just to see this one, semiconductors are semiconductors. Semiconductors are what whose conductivity is more than insulator and less than conductor. They are known as semiconductor. Semiconductors are those whose conductivity is more than insulator and less than conductors. Actually, there are three kinds of materials available. Actually, there are three kinds of materials available. One is conductor, one is semiconductor, and one is insulator. Materials are of three types actually. Either they are conductor, either they are insulator, and the third category which we will discuss in this unit is your semiconductor. So first is insulator. As the name implies, what is the meaning of insulator? Insulator are those which cannot provide the flow of current from them. Okay, they are not the conductors. They are not electrical conductors. Means no current will be flow from the insulators. So like the bamboo stick. The second one is conductors. Conductors, as the name implies, they are capable for the flowing of current from them, right? They are conductors, like iron stick we can say, any wire we can say. But if wire is coated with a plastic, then if we put our hand on plastic, we cannot feel the shock because plastic is insulator. Plastic is not a conductor anymore. That's why. So plastic, bamboo stick, they are insulator. But the iron rod, any wire, they are conductors. The third one is your semiconductors. Third one is semiconductors. Generally, there are two kind of devices available in the world. One are DC devices and one are AC devices. If we simply classify the electronic and electrical world, then what we can say, the devices which are work on AC alternating current, they are electrical devices, and the devices which are work on DC power supply, they are DC devices. They are DC devices. So in AC and DC devices, they are electronic devices. Those work on DC, they are electronic devices, and those who work on AC, they are electrical devices. So in those electrical and electronic devices, basically we use the AC and DC. Here, when we talk about those electronic devices like the transistor, like the diodes, gate turn-off thyristor, silicon control rectifier, metal oxide semiconductor field effect transistor. These are several types of electronic components. So those components are made from semiconductor families. These are semiconductors. So semiconductors are used for electronic devices generally. So semiconductors are the third category, which is not an insulator and which is not a conductor. It is in between them. It is conductors more than insulator, and it is insulator. Okay. Right. So the conductor, these are not the conductor, these are not the insulator. So we talk about the semiconductors first of all. So what is the semiconductor? Whose conductivity is more than insulator and less than conductor. Now I am talking about how many types of semiconductors are there. How many types of semiconductors are there? So basically there are two kind of semiconductors. One is known as pure semiconductor and one is known as impure semiconductor. One is known as pure semiconductor and one is known as impure semiconductor. Here, and the second one is, but whenever we talk about the technical language, technical words, then we cannot use those abbreviation like pure and impure. We use the word as intrinsic semiconductor, intrinsic semiconductor, and the impure semiconductor are known as extrinsic semiconductor. Pure semiconductor are intrinsic semiconductor and impure semiconductors are extrinsic semiconductor. Okay, I just save this file. Pure semiconductor, impure semiconductor. Basically, for the semiconductor, which materials we used for the semiconductor? Germanium and silicon in its pure form. In pure semiconductor, which kind of material we basically used? We basically use silicon and germanium. Silicon and germanium. Pure silicon and pure germanium. I just write down their name also. Silicon and germanium. Okay. So silicon and germanium are basically used as a pure semiconductors. Why we use generally the silicon and germanium? Because they are tetravalent valency. It means the outermost orbit consists of 4 electrons, which is a necessary criteria for the semiconductor materials. Okay. So silicon and germanium are basically used. Silicon atomic number is 14 and the germanium atomic number is 32. So in case of orbital, we can classify them like this one. Silicon comes in the periodic table at the number of 14. Okay, so we can say it is 1s2 1s2 2s2 1s2 2s2 2p6. As you know, as you have already been studied in chemistry also, how to classify the atomic number in orbitals. So 1s2 2s2 2p6 3s2 3s2 and 3p6. you able to hear me, then type in message box okay. No need to say anything, just type in message box okay. Yes. Now see. Yes. So semiconductors are of two types. One is pure semiconductor, second one is impure semiconductors. And the materials which we use in semiconductors to build the semiconductors are generally silicon and germanium. So I just write down the name of those materials once again: silicon and germanium. Okay. The outermost orbit electron equal to 4, that is tetravalent. Tetra means 4. Okay. Silicon at 40 number is the number, atomic number, and for the germanium it is in periodic table at 32. It is in periodic table at 32. So now we see the orbital of those silicon and germanium, because we know that SPDF are those orbitals which are present for any element of the periodic table, SP, D, and F. Okay. So when you divide it in them, then 1s2, the first orbit is always 1s, second orbit is always 2s and 2p, third orbit is always 3s, 3p, and 3d. Fourth orbit is always, we know that 4s, 4p, 4d, and 4f. Okay. But here we do not require for the silicon, so I do not write down here. Now I just put the number of electrons in those cells. So as we know that in s orbit the maximum number of electrons present is 2. Here in second orbital s consists 2 and p consists, the maximum capability of the p is 6, then 3s2 and 3p. It capacity is 6, but it only hold 2. Why? Because we only require 14. So 2 plus 2, which 2 I am adding? Just to see from this red color, this 2 plus 2 plus 6 plus 2, that is 2 plus 2 plus 6 plus 2 is 12, then more 2, 14. So now 14 is completed, so we don't require this 3D. Okay, so which one is the outermost orbit for silicon? The last. This is first orbital, this is second orbital, and this is the last, third orbital. Okay, so the last orbital is known as the outermost orbit of any element. So what is the number of electron in this orbit? 2 plus 2, that is 4. So how, whenever we want to represent a silicon, how we can represent? We just encircle, just write down silicon there. Silicon there, and mentions 4 dots over there. Mention 4 dots over there. The dots are for those electrons. One dot, 2, 3, and this one is 4. Okay, so these 4 dots, actually dots there, so these 4 dots are used for net keys. Okay, and similar, so this is a pure semiconductor silicon. Now similarly for germanium, just to see, because it is at 32, so 1s and 2s, 2p is the second orbital, and 3s, 3p, 3d, and 4s, 4p, 4d, and 4f. Okay. So now we see for 32. We now see for the germanium. We know that S consists of 2, second orbital S consists also 2, P capability is 6, then third orbital S consists of 2, P consists of 6, D consists of 10. So what is the total? 2 plus 2 4, 4 plus 6 is 10, 10 plus 2 12, 12 plus 6 18, 18 plus 10 28. But we require 32. So 4s consists of 2. 4p capability is to hold 6 electrons, but we only require 2 more because 32 is the total sum, and we don't require 4d and 4f in those orbitals. 4p and 4d in those orbitals. Okay. So now we count them. Let count them. With this green color, just see this 2 plus 2 4, then plus 6 10, 10 plus 2 12, 12 plus 6 18, 18 plus 10 28, 28 plus 2 30, 30 plus 2 32. Okay, so now we know. Now we see the outermost orbital. This is first orbital. S and P is the second orbital. Third SPD. So this is the third orbital. Now this one is the last orbit. This one is the last orbit. What is the number of electrons here? 4. Again 4. Similar to germanium, it will be looks like an encircled germanium. This is germanium element. Okay, and our 4 electrons will be at outer side. First, second, third, and fourth. Okay. So now these are silicon and germanium. These are pure semiconductors, and the outermost orbital is known as the outermost orbit electrons is known as valence electrons. So we can say pure semiconductor are those elements of the periodic table which consist of valence electrons. Valence electrons means what? You understand the technical word valence electron? The outermost orbit electron. The outermost orbit electrons. Outermost orbit electrons. They are known as valence electrons. So which consists the valence electron is equal to 4. Those elements are basically used for the pure semiconductors like silicon and germanium. There are too many elements are also available which whose valency is 4, whose valence electrons, number of valence electrons are 4. But we only generally prefer silicon and germanium, and among those silicon, because there are temperature handling capability, power handling capability, their durability is very good compared with all other elements. Among those silicon and germanium, if we compare those elements, then one of the most basic reason, one of the very important reason why silicon is preferred over germanium is that silicon is made from silicon dioxide. Silicon we just find from silicon is mined from silicon dioxide. Silicon dioxide, and that is easily available, vast availability. Silicon dioxide. Silicon is found from silicon dioxide, which vastly, any very excessive quantity, very vastly available. So due to the vast availability of the silicon dioxide, we can easily find silicon. This is one the reason why silicon is preferred over germanium. The other reasons are temperature handling capability, durability, power handling capability, and so many reasons are also available. Now, How many types of impure semiconductors are there? How many types of impure semiconductors are there? Now, one of the most important thing which I'm going to tell you, which semiconductor devices like radios, like transistor, like diode, all those elements consist of some semiconductors. So they are pure or they are impure. Which semiconductor are used? Then remember that always use impure semiconductor. Always we use the impure semiconductor, not the pure semiconductor. For example, if I just give you a very rough example, a very general example, let's suppose someone asks you to make a tea. If some guest come at your home and your mother asks you that just make the tea, you go and make the tea. So you use milk, and some water is also mixed with that milk. Otherwise, if you just make a tea from the pure milk, some persons do not like it because it is not too tasty compared with the milk plus water tea. Is it clear? For example, if someone you ask your mother that just cook a vegetable, okay, lady finger vegetable. Your mother makes a vegetable and give you, serve you, but you don't like if no salt is added in that. If no salt is added in that, so salt, you didn't say your mother that mother cook give me vegetable with salt, but your mother already understand that if my son asks me for preparing a vegetable, I have for the taste I have to make some salt in that. Okay, so it means instead of pure things, some impure things have their value more. Is it clear? Similar to these rough examples, in case of semiconductors, those extrinsic semiconductor which are impure semiconductors are basically used for the making of components. Okay. Now, how many types of impure semiconductors are there? See very carefully. So, impure semiconductors are of two types. Now, listen me carefully. Uh, in some videos, sometimes whenever we just make the video, sometimes due to the light connections are cut off for 5 minutes break, the recording is paused. Okay, so when you will see the recording on YouTube, you will see 5 minutes continuous, nothing is here. So don't be confused from that. You just wait, and after that it will be run like today due to light interruption. Okay, so there are two kind of impure semiconductors are there. One is P type and one is N type. Now, first of all, what is the meaning of this impure semiconductor? First of all, I am telling you about what is the meaning of this impure semiconductor. So now see here. For making the impure semiconductor, either it is P type or either it is N type, we use a pure semiconductor, means intrinsic semiconductor, and then add some impurity in it, means a pure lady finger vegetable plus some salt. That is your impurity, for example, but it will make tasty vegetable. Okay, so plus some impurity will be mixed. Which kind of impurity? I just give you examples. Impurity. Then as a result we will find extrinsic semiconductor. As a result we will find extrinsic. In intrinsic semiconductor, some impurity will be mixed so that we will find some extrinsic semiconductor. Okay, this process of making the extrinsic semiconductor with the help of mixing of impurity, this is not known as a mixing. Actually, this process of intrinsic semiconductor mixed with impurity is actually known as doping. The standard technical word for this is doping. So doping is the process by which we can add some impurity in the pure semiconductor or intrinsic semiconductor so that we will find as a result extrinsic semiconductor. Okay, now see which kind of impurity we mix. Actually, we mix trivalent or pentavalent impurity. Actually, we mix trivalent or pentavalent impurity. You just see very carefully what I am going to teach you. Just see very carefully. I just remove this one. Shift it there for a second. Now you will see. What I told you, intrinsic semiconductor, it means what? Silicon or germanium, because I told you that intrinsic semiconductor means silicon or germanium. So as an intrinsic semiconductor, either you use silicon or you use germanium. Generally, silicon is preferred. Okay. Then the second thing is what? Add some impurity. So which kind of impurity we mix? So either we mix trivalent impurity or pentavalent impurity. Remember my words. As a impurity, always either we use trivalent impurity or pentavalent impurity. What is the meaning of trivalent and pentavalent? Pentavalent means those elements of the periodic table which consist the outermost orbit electron is equal to 5. And what is the meaning of trivalent impurity? Trivalent impurity means those elements of the periodic table which consist the outermost orbit electron, that is valence electron, is equal to 3. I will give you the example completely. You just hear me out first of all. I just write down here which kind of impurity you will mix. Which kind of impurity? Either trivalent or pentavalent. Okay. For example, I am okay. Let's suppose I just add a trivalent impurity. If I add a trivalent as an impurity, then I will find an extrinsic semiconductor. Which extrinsic semiconductor I will find? Because I know extrinsic semiconductor are of two types. One is P type and one is N type. One is P type and one is N type. So which kind of impurity I will find? Because there are two types of semiconductors. So when I mix the trivalent impurity, I will find a P-type semiconductor. P-type semiconductor. Kindly wait. Yes. So as an impurity, either we use a trivalent impurity or pentavalent impurity. If I mix in pure semiconductor means intrinsic semiconductor, silicon or germanium, it means. And as an impurity, if I mix a trivalent impurity, then which kind of semiconductor I will find? I will find a P-type semiconductor. But here now I cannot use the word mixing. What I have to say as a standard definition, in intrinsic semiconductor, if I dope a trivalent impurity, then I will find a P-type extrinsic semiconductor. I will find a P-type extrinsic semiconductor. So in a simple language, we can say this is a basic formula. This is a basic formula for a p-type semiconductor. Okay, this is a basic formula for a p-type semiconductor. Yes. Okay, and what is n-type? Similar to this, an n-type semiconductor is that in which silicon or germanium, that is intrinsic semiconductor dop with a pentavalent impurity instead of trivalent. Here now the impurity is pentavalent. You just wait for some time more. I know your time is completed, but we have to complete whatever I have to teach right today. On yes, so when I mix a pentavalent impurity, as a result, I will find an n-type semiconductor. Yes. So this is a basic formula we can say for the n-type semiconductors, right? So whenever a trivalent impurity is mixed, now how we can mix? How we can say that it is mixed or not? How we can say it is mixed, right? So see how it will mix. How I remove this right hand side. Completely to show you the next things. Now see, let's suppose I want to make a p-type semiconductor. Let's suppose I want to make a p-type semiconductor. Okay, let's suppose I want to make a p-type semiconductors. It means I have to add in intrinsic semiconductor, silicon or germanium, with trivalent impurity. Now, first of all, you just give your answer of the question which I am going to ask you in the message box. Let's suppose you want to build any vegetable. Okay, so impurity is, let's suppose, salt. So whose quantity is more, vegetable quantity or salt quantity? Which quantity is more, vegetable quantity or salt quantity? Yes, vegetable quantity, definitely. It means similar to that, impurity should be low and the original term should be high. It means silicon are more and impurity is low. First of all, what is the meaning of trivalent impurity? Whose outermost orbit electrons consist 3 electrons. For example, boron. For example, boron. Boron is an example of trivalent impurity. What is the atomic number? Hydrogen, helium, lithium, beryllium, and the fifth number is boron. So atomic number is 5. So let write down the orbital for the boron. First orbital is 1s, second is 2s, and then 2p. Okay, now see. Okay, so s consists 2, then second s consists 2, p only consists 1 here because we only require 5. So 2 plus 2 plus 1. Okay, I just see 2 plus 2 plus 1. Okay, so which one is the outermost orbital? This is first orbital, this is your first orbital, and this is your second orbital. Only 2 orbitals. So which one is the outermost orbital? This one. And what is the number of electron in outermost orbital? That is 3. It means this is the boron consists of 3 valence electron. Outermost orbit electrons are known as valence electron, as I told you. So it means boron is trivalent impurity. So whenever you want to show the boron, how you will show the boron? Like this one. This is impurity because you have to use it as an impurity. It means its quantity is low and vegetable quantity, it means silicon quantity is more. So boron is this one. And because the outermost orbit electrons are 3, outermost orbit electrons are 3, it means how many dots are there? 3 dots. 1, see very carefully. 2, and this is 3. Okay. Now we just consist a smaller section of silicon mixing with boron, only one part. Otherwise, the whole silicon consists of a single, for example, a stone consists of several small stones in it. Okay, I am teaching you right now about a small section of a stone. Okay, so this is a small section in which how we can add the silicon with the how we can dop the silicon with the boron. So boron consists 3 electrons because as you gave me the answer that the vegetable is more. Similarly, we want to mix in silicon. The impurity is boron. So boron is low and silicon is more. So this boron is totally at the 4 side. There are silicon. Silicon is more and boron is low. This one is silicon. This one is silicon. This one is silicon. Vegetable quantity is more now, it means silicon quantity is more. So silicon. Okay, and we know that silicon consists of 4 valence electron. So here first, second circle, third circle, and fourth. Okay. Okay, again and again, why should I draw? I just remove this. And just focus. Yes. So now what will happen? Boron consists the outermost orbit electron is equal to 3. Silicon consists the outermost orbit electron 4. We just mix in silicon. We just dop in silicon the boron. So boron is low quantity and silicon is of more quantity. So we can draw like this type of structure. Now what will happen? Before that, I will teach you till 1 o'clock. So kindly wait for a while. Okay. So what will happen? See. Yes. So now see what will happen. Before that, just give me an answer of one question. Now see on the screen. Let's suppose there are 2 persons. Let's suppose there are 2 persons. One is Ram, which have a 5 rupees note and 10 rupees. Okay. And the second person is Ravi. It consists a 5 rupees note and 20 rupees note. Okay. Ram consists of 5 rupees and 10 rupees, and Ravi consists of 5 rupees and 20 rupees. Now, what they do, what they do, kindly wait for a while. Yes. Yes. So 5 rupees and 10 rupees now. Okay, what they do? The Ram gives 5 rupees to Ravi, and Ravi give the 5 rupees to Ram. Ram give his 5 rupees note to Ravi, and Ravi give his 5 rupees note to Ram. Now give me the answer of my question. Is there any exchange done? Is there any exchange done? And my second question is, due to that exchange, is any effect or no effect? Is there any exchange done? Some communication done? And second thing, due to communication, due to that exchange, anything change or not change? Just write down your answer in message box. Yes, exchange is done, but it doesn't have any change. Very good, Nisha. There is exchange but no change. Very good. No exchange, no change. No. For me, no exchange, no change. Why you write down no exchange? Exchange is done na. Exchange means one. Exchange is what? Transformation. Okay, so exchange is done, but no change, but no effect yet. Yes. So you all understand this thing that exchange is done, but no, nothing is happens. Okay. Only 5 or 4 persons just writing down their answers always. Why it happens? Yes, you should write down. All of you should write down the answers. Exchange is done, but no effect, but no changes. Okay, so this is what this kind of exchange is known as. This kind of exchange is known as covalent bonding. Apart from that example, what I want to teach you right now, I want to teach you from this example that what do you mean by the term covalent bonding. This is known as covalent bonding. It means exchange is done, some bonding is done, but without any effect. Without any effect. So see, these 3 electrons, this boron consists of electron, silicon consists of electron. So these 2 electrons together make, no, I just use another color so you will understand. So these 2 electrons makes a covalent bonding. Okay, no change. These 2 electrons make a covalent bonding. So no change. These 2 electrons makes a covalent bonding. So no change. But now silicon consists electron, but boron do not consist any electron. So how they make the covalent bonding? To make the covalent bonding from the other side, because I told you this is one section of that silicon germanium plus trivalent. For example, in a vegetable of peas, matter in a peas, vegetable of peas, I just show you 4 element of peas, silicon, or 4 marbles of peas, and boron is your 1 particle of salt. Okay, but there are too many particles in a vegetable bowl. Okay, so from other side, one electron, because it require 1 more electron, because boron only consists 3 electrons, so 3 side it makes a covalent bonding, but 1 more side is there. So to make the covalent bonding from some other side, electrons will be break, and electrons will move and come here. Okay, and after coming here, they will be able to make a covalent bonding. Okay, so what I want to say that because boron consists only 3 electrons, so 3 sides they make the covalent bonding, but here from other side 1 electrons will come from the other side, because it needed 1 electron, and then makes a covalent bonding. So let's suppose this electron comes, this electron will go there, okay, and now create a covalent bonding. But what will happen? Yesterday I told you that whenever any electron move from one place to another place, because this electron will move now from this side to here, so what will be left there? What will be left there? They left a free space. They left a free space, and this is known as hole. This is known as hole. A free space is there because previously there was electron, but now electron move there. So here free space, and this is known as hole. This is known as hole. Now see very carefully. Now see very carefully. Similar to this making of holes, there are so many silicon particles are there. There are so many boron particles are there. At each time, each boron particle require one electron, so that the complete covalent bonding will be happen from the all the four sides. So there are so many holes will be generated. So because holes are positive charge carrier, because holes are positive charge carrier, because holes are positive charge carrier. So what will happen? So many positive charge carrier will be generated in that semiconductor. Okay, so many silicons are there, so many borons are there. Whenever one boron want four side covalent bonding, it need one electron. It means from any other side one electron will be come here. So whenever electron come here, holes will be generated there. It means positive charge carrier will be generated there. Similar to this is one section. Now at another section, one more electron is needed by boron. So one more positive charge carrier will be generated. So many positive charge carrier will be generated. It means p-type semiconductor consists majority charge carrier as holes. Majority charge carrier means charge carrier are of two types. One is electron, they are negative charge carrier, and one is holes, they are positive charge carrier. So which charge carrier are generated more? Because here holes are generated more. So p-type semiconductor consists one thing. P-type semiconductor consists one thing, that is majority charge carrier as holes. You completely see to the topic. Majority charge carrier as holes, because so many holes will be generated there. Okay, I'm talking about the p-type. If you remember the today class, you will never ever repeat in this unit. The p-type semiconductor, I'm talking about the p-type semiconductor here in this box, because first I add the trivalent impurity. It means I want to discuss about the p-type semiconductor. So p-type semiconductor consists majority charge carrier as holes. Okay. Now there are too many electrons was there. Previously, before this combination, there are too many electrons, but now too many holes are there. It means electrons are now decreases. Electrons are now decreases. It means minority charge carrier. So in p-type semiconductor, minority charge carrier are electrons. Minority charge carrier in case of p-type semiconductor are electrons. And the third one, see very carefully this term. See very carefully. Now see this boron. This boron is what? From all the four sides it is tightly bounded, so it cannot move. Now this boron cannot move. The boron cannot move from one place to another place. Why? Because it is from the fourth side, it is tightly bound by a covalent bonding with silicon. So it cannot move. Cannot move. The boron cannot move. And the thing which cannot move is known as immobile ion. It cannot move. It means it is an immobile ion. So p-type semiconductor consists of immobile ion. Which kind of immobile ion? Now see. In any material of periodic table, in nucleus, nabik, in nucleus, number of proton is equal to number of net negativity is equal to net positivity. We can say number of proton is equal to number of neutrons. Okay. Now here boron, to make the covalent bonding at this side, just to see from this orange color I am talking about here. To make the covalent bonding here, it uses electrons. It means negativity is more, because previously the outermost orbit electrons consist only 3 electrons, and it was in the original boron form. So in nucleus, net positivity is equal to net negativity. But to make the covalent bonding, this boron use a electron to make the, from another side it use a electron. So electron is negative charge carrier. So which thing is increasing, positivity or negativity in boron? Because boron use a electron, it means negativity he use, it means negativity is increase. So it is a negative immobile ion. It is a negative immobile ion. A boron is a negative immobile ion. It is a negative immobile ion. So boron, so it means p-type semiconductor always consists 3 things. One is majority charge carrier as holes, minority charge carrier. Minority charge carrier means charge carrier which are in few quantity. कम संख्या में इलेक्ट्रॉन होंगे. मेजोरिटी चार्ज कैरियर मीन्स ज्यादा संख्या में. सो मेजोरिटी चार्ज कैरियर ज्यादा संख्या में होल्स होंगे. और थर्ड कौन सी चीज होगी? इज द थर्ड थिंग नेगेटिव immobile ion. Okay, so 3 things always hold by p-type semiconductor. Whenever anyone explain you that explain the p-type semiconductor construction, yeah, explain the p-type semiconductor, then you have to show this kind of example, that silicon we just made a trivalent impurity like boron, then due to covalent bonding requirement, one more electron it required from any other place, so hole will be generated there. So now it is tightly bound, so it is a immobile ion because it uses a electron, it means negativity he use, that's why it is a negative immobile ion. Because holes are created too much in this semiconductor manufacturing, that's why a majority charge carrier are holes, and due to holes are increasing, it means electrons are decreases, that's why minority charge carrier are electrons. So now whenever you want to show any p-type semiconductor, how you will show them, how you will show that it is a p-type semiconductor? So you just draw a box type structure. Okay, electrons are shown by dotted. Electrons are shown by dotted. So one dot, second dot, like this one. These are electrons. These are electrons. These are electrons. So because minority charge carrier are electrons, so let's suppose electrons are like this. Holes are shown by circles. Holes are shown by smaller circles. But holes are majority carrier, so you should do more number of holes. And which is the third thing? Third thing is negative immobile ion. How you show the negative immobile ion? Now see very carefully. A negative sign and encircled. A negative sign and encircled by a circle. This encircled show you a negative sign, just encircled by a circle. This encircled show you that it cannot move. It cannot move. And negative means negative without moving element, without moving ion. That is negative immobile ion. Okay. So how you will show? Just show me in a very thin manner. Yes, so this is negative immobile ion. Now we have to draw in this. So in a few quantity, negative immobile ion should be there. this one. This one. This one. So there are more number of holes, less number of electrons, and very few numbers of negative immobile. So this is now the representation of a p-type semiconductor. This is what? This is your p-type semiconductor. Now the p-type semiconductor is completed. How we can make this p-type semiconductor? Okay. Now similar to this, the n-type semiconductor will be made from the mixing from the doping of pentavalent impurity, that is of phosphorus. So in tomorrow class, in next class, I will teach you how the n-type semiconductor will be made. Now, thank you for watching the video, and I hope you understand. Now let's discuss about your problems. Okay, thank you very much.